Hi there, this is Ezra, and this is my project for Intro to Fluids. I specifically wanted to look at the magnetic Reynolds number in Jupiter's plasma sheet. So that's basically the disk of plasma outside of 10 Jovian radii out to about 40 or 50 and even beyond. For this, I looked at basically 10 to 40. So that magnetic Reynolds number, very similar to the classic Reynolds number. The main difference being that instead of the viscosity of the fluid, we're bringing in the electrical conductivity of the plasma in this case, and also bringing in the magnetic permeability constant. Otherwise, just brings in the velocity and the characteristic length in the same way. So just getting a feel for what would happen at high or low Reynolds magnetic Reynolds number. If this number were to be much less than 1, what would happen is the magnetic field would basically diffuse away, and you would just essentially be left with the diffusion equation here. The alternative being that if the Reynolds number is much greater than 1, magnetic field lines will be frozen in to the plasma. And so they'll move along with the flow, the field lines. And this is indeed what I see a lot in the literature. Like, this gets talked about a lot. It's definitely the gyro radii of the ions move along these frozen in field lines. So I'm definitely expecting to see Reynolds numbers greater than 1. But we'll find out. And so just trying to get a feel for what I might expect as far as what this number would be. I looked at a few studies just to kind of see what would be in the ballpark. There's some nice studies done with liquid metal here on Earth, of course, and those Reynolds numbers ended up being like 10 to the -2 or so. Some folks did some work with the plasma sheet on Earth, and they're getting around 500 or so, so a much larger number there. I also found a nice study. Some folks did some work on the interior of Jupiter, and what they see is that getting roughly 220 or so, looking at the dynamo, the metallic hydrogen core, and whatnot. So these just give me some numbers to have in mind. And so first thing I need to think through is, what should the characteristic length be? There's a number of ways you could tinker with this to kind of get some different results. What I chose to do here is to assume that the plasma sheet has a negligible thickness. I think in reality it does have a reasonable thickness of a couple RJ, Jupiter radii, but for simplicity I'm going to make it negligible. And then so if I were to treat this sheet as semi-infinite and just a horizontal plane, it makes sense to just look at the scale of the leading edge. So in this case, it would be like a half of the circumference. So the leading edge of that sheet at each different radial distance that I look at. So what I'm going to do is look at a handful of different radial distances from 10 to 40 RJ. And so the characteristic length scale that I'm going to use is basically half of the circumference at that radius. So I'm just going to go with pi r. And so as far as the velocity of the plasma goes, I have in situ data from the JADE instrument on the Juno spacecraft. So with protons and heavy ions, primarily sulfur and oxygen. And so I'm going to take an average of these two. They're pretty close. Protons tend to move a little faster, being lighter, but all in all, they're pretty close. So I'll take a point between them and get the magnitude of this velocity from the three components. And so I'll do this with each radial distance. So here's kind of an example of what a bit of that data looks like. Here's just one segment of an inbound orbit from 19 to 20.5 Jovian radii. At the top, we got the density. This is heavy ions, by the way. Then there's 3 components of the velocity there, temperatures at the bottom there for good measure. So here I'm going to use the 20 RJ point, and I'll make a few more plots for several other radial distances. And so then also we need to derive the conductivity of the plasma, which will change with radial distance, primarily because the density of the plasma is going to change. And so I can get that electron density. I have that data as well. The main piece that I needed to decide here was what to do about this collision frequency. And I ended up simplifying it, making sort of a guess of 1 based on the densities that we're seeing, and it just seemed like a plausible thing. And of course, simplifying with 1 just makes it a little easier. So I just went with that for new. And the rest of these are self-explanatory. So I was able to put the conductivity together for each radial distance. And then, so having done that, I've got a table here of these values at 10, 20, 30, and 40 RJ. I tried to get as close to the centrifugal equator as I could because that tends to be where the plasma sheet lives. And so running these calculations through, the rightmost column here is the sort of the back of envelope result that I get for the magnetic Reynolds number. Closer in is a higher number, which makes sense because we have a larger conductivity in there because the density is higher. We also have a little bit higher velocity closer in. What we see is that there's some co-rotational lag as we move further out. Not drastic difference in that velocity, but a difference nonetheless. And then so what we kind of see is that obviously we drop off by a couple orders of magnitude from 10 to 40 RJ, but maybe we're tending to level out beyond 30. So a few more data points would probably help really solidify that. But if we plot up those 4 points that I've done here, this is the result that we get. And so all in all, I would say that these numbers are, first of all, within reason. They're not completely disparate from some of those other studies and some of those magnetic Reynolds numbers. And in addition, we stayed above 1, which indeed we're hoping to do because we're quite sure that the magnetic field's not diffusing away anywhere near Jupiter. So seeing that stay above 1 is a good sign, and leveling off outside of 30 is sort of an interesting result that I didn't necessarily expect. So that's it. Thanks.